Okay, so we're going to start with some review of what we learned how to do last week, which was to calculate the pH of solutions of strong acids and strong bases. All right, and so that's where we're going to pick up today. I'm going to give you guys a few minutes, see if you can't calculate the pH of these two solutions. One with a concentration of hydrochloric acid equal to 0.5 molar, and the other sodium hydroxide equal to 0.5 molar. All right, what are the pH of these two solutions here? All right, so my approach here, we know something very important about this acid, hydrochloric acid, which is what? It's a strong acid, right? It falls into that bucket of being a strong acid. And because it is strong, that simply allows us to say that the concentration of that acid is going to be equal to the concentration of the hydronium ions in solution. All right? So then if we're looking for pH, we can take a look at, all right, I guess we know this is that 0.50 molar. So if we're looking at pH, we need that equals negative log of the concentration of hydronium ions. We're just going to plug in that value that we have for our concentration of hydronium ions, that 0.5 molar. And our calculator spits out 0.3010299, et cetera. And what are our units on pH? Yeah, trick question, right? So we don't have any units for pH here. We do have our annoying new sig fig rule, and that is that these two sig figs in my concentration are going to correspond to two decimal places in my pH here. So reporting this to the correct number of sig figs, we have a pH equal to 0.30, no units. Okay, so again, the key part here is that hydrochloric acid is a strong acid. So just by knowing the concentration that I had initially, I know my concentration of hydronium in solution. And we get to say a similar thing for sodium hydroxide. This is also strong. And because it's strong, I get to say that my concentration of NaOH is equal to the concentration now not of hydronium, but of hydroxide, the other one. All right, so I want my pH. We had our pH formula up here, but the problem is in my pH formula, it's concentration of hydronium, and I don't know that. I know concentration of hydroxide. All right, but importantly, what we also learned in addition to our pH formula was what we called our autoionization relationship here. The fact that if you know one of those two concentrations, in this case our hydroxide concentration, you can use this autoionization relationship, the fact that the product of hydronium and hydroxide is always that same magic number, 10 to the negative 14, to figure out what the other one is. All right. We also took that and we put it on a log scale. We practiced with the other one last time, so let's practice with this one here. This tells me that the pH plus the pOH is equal to 14. So what I can do now with my hydroxide ion concentration is calculate that pOH by taking the negative log of the hydroxide ion concentration. And I get that same value we got before because it's that same 0.5 molar. All right, but again, now this doesn't represent the pH, but the pOH. So I'm going to have to use the fact that pH plus pOH equals 14. And how would I get that pOH over to the other side? What would I do? Subtract. All right, so this would just rearrange to pH equals 14 minus the pOH, which if I punched into my calculator would be 13.70, rounded to the correct number of sig figs. And that should check out, right? I have a basic pH for my strong base solution. It's above 7. If we look for our hydrochloric acid, 0.3, that's a low pH, which makes sense. Low pH is the acidic region. Cool. All right, so that was strong acids and bases. And now we're going to talk about our other bucket here, the weak acids. We'll get to weak bases here in a second, but let's start with weak acids. All right, so first of all, what we were introduced to last class was this, what we called our acid dissociation reaction. These are the ones that get that special value for their equilibrium constant, Ka. All right, so I'm going to put down an acid here, C2H3O2AQ. All right, this is going to be my acid in this chemical equation here. And in our acid dissociation reactions, we always have our acid with what other reactant? Water. So this is when we take our acid and combine it with water. And in this case, since I'm mixing it with this acid, water will be playing the role of the base. All right, so everybody take a second. Give me this balanced chemical equation for our acid dissociation reaction. All right, so if I want the formula for my conjugate base, which one of my reactants am I going to look at, my acid or my base? My acid. So my acid will tell me what my conjugate base is. I need to take away a hydrogen. And I'm going to need to take away a charge, right? So now it goes from being neutral to having a -1 charge. In order to get my conjugate base, my conjugate acid, I'm going to look at my base. All right, water, when it plays the role of a base, is going to accept a proton, increasing the number of hydrogens by 1 and increasing the charge by 1, giving us, we got a special name for this one, the hydronium ion. All right, so in our acid dissociation reactions, we have an acid plus water, gives us whatever our conjugate base is, and we always get that same other product, hydronium. Okay. All right, so we looked at this chemical equation before when we were talking about acid strength. Specifically, we looked at it for a strong acid, hydrochloric acid. And what we said made a strong acid a strong acid, what makes hydrochloric acid a strong acid, is the fact that this reaction right here goes 100% to completion, right? That's why we were able to make that assumption that we made in that practice problem we did, where the concentration of HCl that we started with is equal to the concentration of hydronium at equilibrium, because every bit of this reaction takes place. Very strongly favors the products. All right, now though we've switched our discussion to weak acids, and weak acids are considered weak because they do not fully dissociate. Meaning our dissociation reaction right here, we don't want to represent with just this one arrow, making it seem like all reactant gets converted to product. Instead, we have to pay attention to the equilibrium in this reaction. So we want to use our fancy little double-headed arrows. All right, so what's going to make weak acids different than how we treated strong acids is that these are going to be equilibrium problems. We're going to have to dig back into what we learned in the previous chapter in order to solve these weak acids. All right, so what do I mean by that? Let's lay down an example problem here. What is the pH of a 0.50 molar solution of our acetic acid? That's the name of this particular acid. All right, and let's just take a step back for a second. If I'm asking for the pH, which one of these species in my balanced chemical equation am I working to quantify here? My product, my hydronium ions, right? That's the name of the game here. How much of this reaction has occurred? How many hydronium ions have been created? Because if I know that, I can figure out what the pH of that solution is. All right? And like we said, this is going to be an equilibrium problem. And we have this special little symbology we use for our equilibrium constant for our acid dissociation reactions, Ka. But again, it's just an equilibrium constant like we learned how to build last chapter. So everybody's going to take a second and they're going to give me this Ka equation here. All right, for our balanced chemical equation here, what does that equilibrium expression look like? All right, so equilibrium expression, what are we going to chant to ourselves? What over what? Products over reactants. And then one of these things in one of these species in my balanced chemical equation is not going to appear in that equilibrium expression at all. Which one is that? Water, right? Because of that liquid designation there. So instead, we're just going to have the concentration of our conjugate base times the hydronium ion concentration, all divided by that acetic acid concentration. Cool. All right, so again, we got an equilibrium problem on our hands. Again, which one of these terms in my equilibrium equation here am I interested in solving for if I want the pH? This one right here, right? The hydronium ion concentration. That's what we're after. Okay, so equilibrium chapter, we learned this new problem-solving strategy. And what was that? A table, yes, exactly, our ice tables. All right, so just like last time, we had to use ice tables to solve our equilibrium problems. Weak acids are another equilibrium problem. So we're going to take our initial conditions here, and y'all are going to build me an ice table. All right, I'm going to give you guys a little bit of a head start, and then I'm going to quietly fill in my own ice table up here. All right, so I built my ice table here. The I in my ice table stands for the initial amount of each of these here. I start out with just that 0.50 molar of my acid. And initially, we have no reaction that's taken place yet. All right, my C box, the change in concentration that happens. Okay, so we use our variable x for this box here. Okay, and then we got to worry about the sign of x. What's the sign of x in my reactants? Negative. We're going to decrease for our reactants. Products will increase. Okay, and then to get my E box, what do? My equilibrium box. Sum them up. So 0.50 minus x times x, or rather x and x. 0 plus x is x, 0 plus x is x. All right? So I have this equilibrium expression here, and I have this ice table. The most important thing to remember about your equilibrium expression is that this only works for concentrations at equilibrium. Right? We can't just plug in any willy-nilly concentrations into there. They have to be the equilibrium concentrations. However, in our ice table, we have equilibrium concentrations. We got this whole row here, right? My equilibrium concentration of my acid, my acetic acid, that corresponds to this equilibrium of acetic acid box on my ice table, right? Same thing with concentration of that conjugate base at equilibrium. That's also on my ice table. And lastly, the thing that I really care about, my concentration of hydronium at equilibrium on my ice table here. So what we're going to do is we're going to pick up each of these expressions and plug them back in to our equilibrium expression, our Ka equation here. So what we get is that Ka equals x times x over 0.50 minus x. All right, plugging everything back into that Ka here. All right, I'm going to condense this numerator here. X times x can be simplified as x squared. Cool. All right, but looking at this equation here, I got too many missing things, too many unknowns here, right? I can't have both missing variables, Ka and x. I got to know at least one of them to have a chance of solving this, okay? Fortunately, for all of the acids, those Ka values are well tabulated, right? These equilibrium constants, so we can tabulate all those constants, and that makes up our constants page for this particular chapter here, all right? What we see is just a whole bunch of Ka values for a bunch of acids whose names and formulas are listed here, right? It's in alphabetical order, so as long as we know what our acid is, we can go and we can look up our Ka value. Again, we were studying acetic acid, so we want to note that value of Ka is 1.8 times 10 to the negative 5. All right, and I'm nice and I give you the names of these acids as well as the formulas, so they're a lot easier to hunt down on this table here, because again, it's in alphabetical order. What's up? Why is there multiple Ks? Oh, so this is a good question. It's because some acids, for example, arsenic acid, has 3 donatable protons. And so each one would have a different Ka value. We're not going to mess too much with polyprotic acids other than to note that fact right there. But nonetheless, that is why you see multiple values on this table, for certain acids only. What's up?
Will we need to memorize any of these for tests?
No, absolutely not. No, that'd be ridiculous. No, so this is on our constants page, and so anything on the constants page you can expect to have on your exam as well, right? So you kind of want to view these as tools, that we're going to learn how to use this tool, and that's the important part. It'll be given the tool, you just need to know how to use it. Yep. All right, so 1.8 times 10 to the negative 5 here. So let's go back and update. Now we know that value for Ka. So I'm just going to note 1.8 times 10 to the negative 5. All right, cool. So this equation here, we're going to learn 2 different strategies for solving this equation. Because quite frankly, you could do it algebraically and it would just be a huge pain in the butt. You would wind up with what would be called a polynomial. You have x squared plus something x plus something else. You'd have to use your quadratic formula, you know, the negative b plus or minus the square root of b squared minus 4ac all over 2a, that business. Anyways, kind of a pain in the butt, all right? So we'll have 2 different strategies for solving this. One of them, we're going to make note of this value of Ka, right? What we looked up, remember, is the equilibrium constant for this reaction here. So I know my equilibrium constant for this reaction is 1.8 times 10 to the negative 5, all right? Well, remember, we learned about equilibrium constants and that these values tell us something about which direction the reaction favors. So a little number like 1.8 times 10 to the negative 5, does that favor our reactants or our products? That favors our reactants. And not only that, but what can I say about this reaction with the value as small as 10 to the negative 5? It strongly favors our reactants, okay? So this equilibrium here strongly favors this reactant side with my acid form, meaning that very little of this reaction is actually going to take place, right? Only a teeny tiny bit of hydronium ion will be formed when this reaction occurs. We'll see nonetheless that has a big effect on pH because pH is on a log scale. All right, but what we can do is we can take that into account to do our first problem-solving method here, what we call our small x approximation. All right, and we can just note here, this is problem-solving method 1. All right, so what does our small x approximation say? Again, x, which I guess we should just note, what is x corresponding to our balanced chemical equation here? X is simply the amount of product that has formed in that reaction, right? Both my hydronium ion and my conjugate base, that's what x is. And again, we stated that since Ka is so small, that value is going to be really tiny. So what this means, our small x approximation is that our initial acid concentration minus x. All right, to be clear, I'm talking about this term in our denominator right here, right? That 0.05 was that initial acid concentration minus x, okay? And our approximation is going to be that this is the same thing as simply that initial acid concentration. Right? Because x is so small, such a teeny tiny number, that when you subtract that teeny tiny number, it doesn't change that much bigger number very much at all. Right? So again, we can approximate that denominator as being just equal to the concentration of acid. So what does that mean for our specific equation here? Exactly, right? So basically, what I'm going to do in my mind is I'm going to look at this and say, all right, I get to ignore this part right here of that denominator. So this is going to be the same thing as x squared over 0.50. All right, and the reason that we're going to do that is because it just makes the algebra 100 times easier. All right, so I believe in y'all. Everybody take a second and tell me what the pH of that solution would be solving this equation here. What's that? Okay.
When you do like, if you have a 10 to the x, but does it matter if you do number times 10 to the x or number 10 to the x?
I don't believe so.
Okay, thank you.
Yep. All right, so in order to get x all by itself, I need to take this equation and multiply by that initial concentration of 0.05 molar. All right, so now I get x squared equals that concentration times that Ka value. And I can get rid of that square by doing square root of both sides. right? So I get x equals the square root of 0.50 times that 1.8 times 10 to the negative 4. All right, which I punch into my calculator, and I get 0.003. Oh, my bad, times 10 to the negative 5, I'm sorry. All right, and so am I done? Okay, so remember, we always at this point, we just did a whole bunch of algebra, and we want to go back and check our ICE table. What we solved for that value of x is our concentration of our hydronium ion. All right, so that 0.003 that our calculator spit out is the concentration in molarity of that hydronium ion. And so in order to get the pH, I got to do one more step, which is to take the negative log of that hydronium ion concentration. 2.52. We're going to just kind of arbitrarily cut it off at 2 decimal places here. With our with our ICE tables, we're not going to try to keep track of sig figs, all right? So I'll just tell you how many sig figs for those ICE table problems. All right, but we have the pH of our weak acid solution here, 2.52. All right, so just to review what we just did here. We want to study these acid dissociation reactions where we take an acid and we put it in water, and we're trying to figure out how much hydronium ion has been formed. What's the pH of that solution? Because this is a weak acid, we have to pay attention to the equilibrium of this reaction. So we're going to build our equilibrium expression, and then we're going to build an ICE table to fill it in. All right, so we take those equilibrium boxes of our ICE table, plug it back in. We need the other part of this equation as well, the left-hand side, our Ka value, and for that, we're going to go look them up on our constants page here. Once we get that, we learned our problem-solving method, our first one, and we'll talk more about this here in a second, our small x approximation, where we're going to say, all right, x is some teeny tiny value, so I'm going to take my initial concentration minus x and assume that that's the same thing as just the initial concentration, or approximate it rather as just that initial concentration. That allowed me to solve for x, which was the concentration of hydronium ions, and then finally get the pH of that solution by taking the negative log of that concentration. Cool. All right. One more thing about this small x approximation that we're going to note here. All right, and that is we have a limit to that small x approximation. Basically, x better be sufficiently small, or all of a sudden that approximation's crap, right? So we need to make sure that x is sufficiently small. So we have this test. What we want is for what we call the percent ionization to be less than 5. Less than 5% ionization. All right, by ionization, I simply mean how much of that dissociation reaction has occurred. So our concentration of hydronium over the initial acid concentration times 100, because it's a percent, has to be less than 5. All right, so let's do our limit test here. Let's go back to our problem. Let's make sure that this works. All right, remember we found our concentration of hydronium. That was equal to that 0.003 molar. All right, our initial acid concentration, we can find that from our problem or from our ice table here. That's that 0.5 molar. We're going to take that, multiply by 100, and we get 0.6. Did we pass or fail? We're good, right? This is less than that 5% cutoff. So our small x approximation is valid here.
Again, we assume this when the Ka is so small it strongly favors the...
We're going to, well, so you can always assume this and then do the test to see whether or not it works. And so what we'll talk about now is a second strategy that we're going to use if it fails.
Okay.
Why, when we assume that x is close to 0, why is the x in the numerator not ignored too?
Oh, because you don't assume it's 0. Otherwise, the left-hand side 0, your equality is all wrong then, right? 0 doesn't equal 1.8 times 10 to the negative 5.
Right.
So you just error out that whole equation real quick by assuming x is 0. We don't assume x is 0. We assume that it's super, super small, right? And that just means that this number, let me see if I can get it, yeah. If x is, so for example, x is 0.003, 0.5 minus such a small value is close enough to just 0.5 that you can use it without messing up the pH calculation,
I see.
right?
Because it's not related by multiplication or division, it makes a little difference.
Correct, yeah, yep. And we'll see it's still an approximation, but it's a good one, basically. We can get away with it and have that good approximation most of the time. And we do this all the time in science. Physics is famous for doing these like small approximation things to make their lives easier, right? So it's just a general strategy that we use in science over and over again. All right, but what we want to do now is I want you to all go through the same process. It's a long process here for a new weak acid, all right? So I'm going to give you all a head start here. Our goal is going to be to calculate the pH. All right, let's ask, what is the pH of a 0.010 molar solution of hydrofluoric acid? All right, hydrofluoric acid is one of our hydrohalogens. It's also the only one that is not considered a strong acid. So this is still considered a weak acid, which means we need to use our weak acid problem-solving strategy. We got a few parts that we need here. We need that acid dissociation reaction. Once we have that, we can build that Ka equation. All right, and then fill it all in using an ice table. Okay, so I'm going to give you all a little bit of a head start. In direct analogy to what we just did with acetic acid, I want you to do these same 3 parts here for our new weak acid, hydrofluoric acid. I'm going to give you a little bit of head start, and then I'll kind of quietly fill in so that if you're stuck, you can look up here. All right, so I've kind of quietly filled in my acid dissociation reaction here, that hydrofluoric acid and water, to make my conjugate base the fluoride ion, and those hydronium ions. Products over reactants to do my Ka expression here, and then I'm going to build my ice table. If you have not already, you can continue on and use that small x approximation to figure out what our pH of our solution is.
Do you have the Ka?
Oh, yeah, we do need that. Sorry. Cool, yeah. So we need to go to our table here, and we need to note it for our particular acid. All right, so HF, hydrofluoric acid, that's 6.8 times 10 to the negative 4. All right, so filling in our ice table into our Ka equation. We get that Ka value, that's 6.8 times 10 to the negative 4, is equal to x squared over 0.010 minus x. All right, again, we're going to first attempt our small x approximation. All right, that means that we get to take this equation right here, and we get to just ignore that minus x in our denominator. So if we rearrange and solve for x, we get x is the square root of that 6.8 times 10 to the negative 4 times that initial concentration of 0.010 molar. Okay, or a value, once we punch it into our calculator, of 0.026,076. Cool. All right, and importantly, according to our ice table, what is that value of x? That is simply our hydronium ion concentration. So if I take the negative log of that concentration, I get my pH equal to 2.58. All right, but before we can sort of move on with our lives, we're going to have to test that limit of that small x approximation. So everybody real quick, let's do our small x approximation limit test, see if this thing passes. All right, so remember that limit test is that concentration of our hydronium ion divided by the initial concentration of acid, that 0.010 molar times 100. All right, we punch this into our calculator. We get 26.1%. So what can we say? Did we pass or fail here? We failed. Okay, so our small x approximation, that was our problem-solving method 1. So what about our problem-solving method 2? How do we get that real value for x? For that, we're simply going to use our fancy calculators. All right, we're going to use that solver feature. So we'll get some more practice using that. If you want to, if you do not have a calculator with that feature and you want to borrow one up here, that'd be great. All right, but we're going to use our fancy solver. All right, so after we fail, instead we need to calculate our real x. And we need to go back to our original equation here, right? We don't get to scratch x from our denominator. We're back to that original one here. Now, if you just love algebra, you can absolutely take this equation and solve it algebraically by rearranging it into a polynomial, ax squared plus bx plus c, and then using that quadratic equation, all right? Or if we don't like algebra, again, we can just use our fancy solver here. All right, so for the sake of demonstration here, let's go through this. I can see that. All right, so again, I'm going to go to my numSolve button here in blue. So I went to second and then hit that to get to numSolve. I'm going to punch in my formula here, that's 6.8 times 10 to the negative 4. All right, on my other side is that variable x. Remember, we need to use that fancy x button down at the bottom. So we're going to do x squared divided by, and then so I don't mess up my order of operations, I'm going to put in parentheses that 0.010 minus x. Close our parentheses. All right. Remember, we need to give it this seed value. It's got to look around a particular value to find our solution here. What we know about x is that it's going to be a fairly tiny number. Right? This reaction still favors the reactants, so we're just going to pick a tiny number here, 0.001. Sure, sounds great. All right, and it doesn't take it much time to find the actual solution, which is 0.00228975, blah, blah, blah. All right, so this solver function here will tell us our actual value of x, where we don't have to make any approximation. So when I'm showing my work here, I'm just going to say I used the solver and found that x was equal to 0.002289, et cetera, et cetera. All right, and then just one more step, because remember, we're not done yet. What we found was our concentration of hydronium. In order to get our pH, we're going to take the negative log of that hydronium ion concentration. Or 2.64. All right, and if we just want to mark that this was our real value here for our pH, if we go and we compare that to our small x approximation value, we can see that they are sufficiently different, right? So I got an answer that was too far off the mark by using that small x approximation. Again, we did our limit test here to indicate that we were too far off, and then we defaulted to our solver function. All right. Cool. So again, our weak acid problem we're going to treat as an equilibrium problem. So we have our balanced chemical equation for these dissociation reactions. We're going to build that equilibrium expression and then solve by building an ice table to fill it all in. Right? Similar strategy that we used for our equilibrium problems in our previous chapter. Okay, in addition to calculating the pH of weak acids, we also should know how to do weak bases. These are very similar, direct analogy here. All right, just like weak acids, weak bases do not fully dissociate. All right, so again, we're going to have an equilibrium problem on our hands. All right, and we talked about these last class period, but let's just make dang sure we understand what equilibrium reaction we're talking about here. These we don't call acid dissociation reactions, but base dissociation reactions. Where we take our base, so for example, our weak base ammonia, and our other reactant is always this same compound. What was it always in acid dissociation reactions? Water, same thing. So this is when we take a base and add it to water. All right, well, the base will be playing the role of the base in the reaction, which means water is going to be playing the role of the acid this time. All right, well, depending on whatever my base is, that will tell me my formula for my conjugate acid. In this case, this ammonium ion, NH4+. But we always get the same conjugate base in these base dissociation reactions, which we got a fancy name for, hydroxide. Okay, in our acid dissociation reactions, we denoted those Ka. For our base dissociation reactions, we're going to use the symbol Kb. And just like before, we can look up our value on our constants page. Just like we have a whole bunch of acids listed, we also have the Kb values of a whole bunch of bases listed as well. All right, so just like before, we'll look in the same location to find the value of that equilibrium constant. Cool. All right, we're going to move on here. We're actually going to go back to where we started this entire discussion, was talking about our conjugate pairs. All right, now that we've had this discussion of acid strength, we want to revisit this concept of conjugate pairs. Let's get some examples down. Again, this was one of the first skills we learned how to do. I'm going to give you the formula of an acid, and you're going to give me the formula of its conjugate base. All right, so the conjugate base of water, we just looked at this in our base dissociation reaction, is that hydroxide ion. Okay, for this formula here, acetic acid, I got to take away a hydrogen. Do I take it away from the front or the middle? The front, right? Never touch the ones in the middle here. Right, and for hydrochloric acid, that would be the chloride ion, would be my conjugate base. All right, so again, we've sort of already talked about strength a little bit, so let's kind of revisit this here. And one of the things I want to focus on now is this word base over here on our conjugate base side, right? Thinking about strength again. So first of all, water, if we add water to water, is it going to change the pH of that solution at all? No. So water would be considered completely neutral, has no effect on the pH of a solution. But what about its conjugate base, the hydroxide ion? What would we classify that as? A base, but not only a base. What else can we say about it? It's a strong base, right? It is the strong base, actually, the only one that we know about up at this point in our chemistry careers here is that strong base, that hydroxide ion. All right, let's look on the bottom row of our table. Hydrochloric acid, what do we know about that one? It's a strong acid. Well, its conjugate base, the chloride ion, if you were to take chloride ions and add them to solution, so for example, take sodium chloride and dissolve it in water, it again has no effect on the pH of that solution. So chlorides are considered neutral. All right, but acetic acid isn't a strong acid. It is a weak acid. And it turns out that its conjugate base, this thing over here, we call it an acetate ion. If you add acetate ions to water, they will change the pH of that solution by acting as a base, specifically a weak base. All right, so let's just note here, we have this trend of increasing acid strength. And we see an exact inverse relationship between the strength of those conjugate bases. All right, and one of the most important things to note here that we just established is that the conjugate base of a weak acid is itself a weak base. Right? Weak and weak are conjugates. Strong and neutral are conjugates, and weak are conjugates. All right? We can just note that we could say the same thing about bases as well. It turns out that the conjugate acid of a weak base is itself a weak acid. So if we flip the word acid or base in that previous statement, it also holds true. All right. In fact, there is a special relationship between the acid strength and the strength of its conjugate base, and we're going to make sure to have in our notes in big letters that this is only for conjugate pairs that this formula will work. But the Ka of an acid times the Kb of its conjugate base is always equal to the same number, Kw, our magic 10 to the negative 14 number. All right, so again, this statement is only true for conjugate pairs. But for conjugate pairs, if I know how strong my acid is, I can find out how strong that conjugate base is, and vice versa. All right, so let's do an example here. Okay, I'm going to tell you the Kb value of our weak base ammonia is 1.76 times 10 to the negative 5, right? I went on that table and looked it up. And what I want to know is what is the Ka of the ammonium ion, its conjugate acid. All right, so I'm going to take that Kw, that 10 to the negative 14. I'm going to divide by that 1.76 times 10 to the negative 5. Right, and I get a Ka value of 5.6818 times 10 to the negative 10. All right, so if I know the Kb value of this base, I can look that up on my table. I can figure out what the Ka of its conjugate acid is. right? Because I have this equation here that works only for conjugate pairs. But if we know the strength of an acid, we can figure out the strength of its conjugate base. Likewise, if we know the strength of a base, we can figure out the strength of its conjugate acid. Cool. All right, one more thing that we're going to add to our notes here. Under our limit test, we said our limit test for our acid, weak acids, was the concentration of hydronium divided by the concentration of acid initially. If instead we were talking about weak bases, I wouldn't be talking about a concentration of hydronium, but a concentration of what? Hydroxide, right? So let's just note that this is our ionization test for acids. And for bases, we would use a very similar, but importantly, slightly different one, where we took our hydroxide concentration divided by our base concentration initially. All right, still multiplied by 100, and still that same cutoff of 5%. Cool. All right, so importantly, today's focus was on weak acids and weak bases. And the big distinction here was that weak acids do not fully dissociate, so we have to pay attention to the equilibrium of our acid dissociation reaction. All right, so looking at our balanced chemical equation here, we're going to treat it as being at equilibrium. And we're going to use our equilibrium problem-solving strategies. We're going to build our equilibrium constant, and then we're going to fill it all in with an ice table. All right? And we got two different problem-solving strategies. Depending on our value of Ka, you'll find that this x approximation, the small x approximation, works better for acids that have very low Ka values, right? Reactions that don't favor the that very strongly favor the reactants. As well as if you have dilute acid solutions that can also mess up this approximation. So the bigger that initial concentration, the better this approximation is. Nonetheless, we learned about using this approximation, but also how to test it here, using our percent ionization. All right, if it fails, then we're going to use our fancy calculator and use that solver feature to solve our equation instead. Cool. And then lastly, specifically for, we look up those values of Kas and Kbs on that table, but specifically for conjugate pairs, we can also use this equation here, where if we know one of them, we can find out what the other one is using this equation, because their product always equals that same magic number, Kw. Cool. Break. All right. We will meet back here for lab at